Well, good evening, everybody, and I'd like to say a very warm welcome to you all. Thank you for joining us for another of our series of the West Midlands Chemistry Teachers Centre Sixth Form Lectures. And tonight I'm very privileged to have my esteemed colleague and friend, Professor Richard Tuckett, who is going to talk on a very topical subject of the climate emergency. So this, a few years ago, used to be called global warming or greenhouse gases. But now, of course, it's called the climate emergency, and Richard will explain why. So Richard, in his latter years on the staff at the University of Birmingham, was a professor of chemical physics. He retired formally in September 2015 and became emeritus professor from October that year. But he's still very active in research and also publishing, and he'll tell you a little bit more about his book, or a chapter of his book that he's writing as well. But Richard's published over 140 research and review papers in the International Literature of Chemical Physics, Physical Chemistry, and he's also received major grants from the EPSRC, STFC Research Councils, the Royal Society, and also the European Union. But his main research areas are in the field of vacuum ultraviolet spectroscopy and unimolecular dynamics of polyatomic gas phase molecules, especially of long-lived greenhouse gases, of which he's going to talk today. He also uses synchrotron radiation from the national sources for these studies and was a dedicated user of the Swiss light source. Obviously, Switzerland was a much more convenient place to go and do his experiments than the UK. I'd imagine the food was a little better there, Richard, and your board and lodgings were. So he was at the Paul Scherrer Institute in Switzerland from about 2008 until his retirement. And I think some of the results there sort of be written up. So still some papers remain to be written. So that's a little bit about Richard. His title, I'm pleased to say, is called The Climate Emergency. What's the science and what should we do? It is about the science, and hopefully Richard is going to talk impassionately about the science, but there are a few of his personal opinions that will come through, and I think a little bit of politics at the end. So it's a very topical subject. Thank you all for joining us. So if I'd like to now invite Richard to share his screen, and you'll be able to see his PowerPoint presentation.
Okay, so welcome everybody, but especially to over 100 year 12s and year 13 chemistry students. My name is Richard Tuckett, as you've heard, and tonight's talk is about the science of climate change and what we should do. It is no exaggeration to say that, in my opinion, this is the most important issue facing planet Earth today, and is orders of magnitude more significant than the current COVID pandemic. But please do not be alarmed. I hope you find these talks both entertaining but also realistic. I hope everyone is comfortable, well fed, and has a drink to hand. Non-alcoholic, of course. We will have a short 3-minute pause halfway through for a comfort break and to replenish glasses. I hope the whole talk will be under an hour, and I have a clock in front of me to guide me. I will try to answer questions at the end, but try is the operative word. You will all be Zoom expert by now, so please write questions as they strike you via the chat facility. The hosts will process these questions, and one of them, I don't know who, will put them to me, I hope very politely, at the end of the talk. This is the first webinar I've ever given, and I certainly miss having 150 faces in front of me. All I have is a screen. But I assure you, I've given talks on this subject many times over the last 10 years, including 5 every other year to the West Midlands Chemistry Teachers Centre. And I will do my best in this new format. So, Mark, does my voice sound okay to you?
It does, loud and clear, Richard. It's holding up very well.
Fine, thank you. So, off we go. the points I'm good. The first part of this talk is going to be science, and then we'll have a quick break, and then we'll talk about what we should do. And I deliberately tried to make this understandable by 16 to 18-year-olds, obviously. And the points I want to talk about are those two. Is the correlation between CO2 concentrations and the temperature of our planet absolutely scientifically proven? Question mark. And if it is, what actions are possible, both individually, nationally, and also internationally? And that's going to be the second part of the talk. I have written about this several times. The first article here, Encyclopedia Analytical Science, that came out last year. That's pretty straight science. Then the book that Mark was mentioning is going to appear as a third edition in early months next year. And purely by good luck, I was sent the proofs of my chapter, which is in fact going to be the lead chapter of this book, literally 2 days ago. So accepting that I haven't yet corrected them, so there may be typos, etc. But Mark will send these proofs on to everybody. And it's there for you to peruse and read and think about. And of course, you won't understand it all. You can't possibly. I sometimes think I don't understand everything I've written, but I try to pretend that I do. But in any case, everybody will get a copy of these proofs. And this talk is basically based on that. Now, something's happened, Mark. What's happened here? There's a red squiggle come across.
Yeah, look, oh, there you go. It looks like you're drawing on the screen, Richard.
I've done nothing. I've done nothing. Oh, well, we'll have to have live with it. Okay. So I last gave this talk 2 years ago, and I do keep copies of these talks, and I just will listen to it, what I said 2 years ago, and things have definitely changed in the last 24 months. We don't talk about global warming now. We talk about global heating. We don't talk about climate change. We now talk about a climate emergency. And emergency is a pretty strong word. And I assure you, although the Birmingham City Council have set a target of trying to get to net zero carbon just in the within 10 years, that is a hell of a target. I don't know whether it's going to be achieved. There is an argument about what that word net actually means. So there's semantics and definitions there, but that's detail. This is the best one. I think that a climate skeptic has become a climate science denier. And I approve of all of those word changes because it makes the whole thing much more topical. And a lot of things have gone on which we should celebrate. Mercifully, the science deniers have disappeared from our media in this country. All they've been replaced by either Greta Thunberg and Extinction Rebellion. And there's a very nice picture from the web of Greta Thunberg. They have different ways of registering their protest about what's going on in the world, and I'm not going to get into that. But these are the people that are in the ascendancy. It is not the science deniers. Alas, that is not yet true in North America, and the current president of the United States, whose name is here, but we live in hope that there will be a change tomorrow. I'm not allowed to say more than that, otherwise I bring politics into a science talk, and that's not allowed. So this was the cover of the first edition of this book that came out in 2009, 11 years ago. The second edition came out 5 years ago, and the third edition is coming out next year, And you can almost see the way my thinking has gone just by the title of the chapters that I've written. I started off talking about the role of gases in global warming, because I would say 11 years ago, you could not say definitively there was a correlation between the amount of CO2 in the atmosphere and the temperature of our planet. I was more certain you could say that 6 years later, so the language was stronger in the chapter, and I talked more about the causes of enhanced concentrations of greenhouse gases and made some mild suggestion about what we might do. And now the chapter is titled The Potential Climate Emergency and what we should definitely think about doing. So that's by way of introduction, and you've got used to me and my voice. So I've got about 6 slides, which are basically about the science of the greenhouse effect. And my experience is that this is taught in many different ways in secondary schools. And this, what I'm about to tell you, maybe another different way, I'm not sure. So it all goes back to 100 years to things called black body curves, which was formulated in the early parts of the 20th century. And Mr. Einstein, here he is walking around on his bicycle, was a great format of this. And here's a picture of him with yours truly. And that's taken up at 4,000 meters in the Alps at an observatory where there's an exhibition to all his work. The black bodies curve basically say that all black bodies emit radiation, which has a distribution that rises and then falls away. Okay, and we're plotting wavelengths going from left to right here, and you can notice it is not a linear, it is a logarithmic scale. And I've got 2 black bodies, the sun and the earth. And of course the sun is yellowish, and we can see that with our eyes, even though it's 93 million miles away, and we are inhabitants of the earth. This is not stale, and there are 2 really important principles. The total emitted energy is proportional to the 4th power of the absolute temperature, and the absolute temperature of the sun is about 6,000 Kelvin. The absolute temperature of our planet is about 300 Kelvin. So this is a factor, Earth is a factor of 20 cooler than the sun. But this is the important one, the second equation. The peak of the black body distribution is maximum wavelength is proportional to the inverse of the temperature. So if the temperature goes down by a factor of 20, the wavelength of a maximum goes up by a factor of 20. Now then, the sun has its maximum in the visible region, which is why we can see it at about 600 nanometers or 0.6 or a micrometer. So if you multiply that by 20, you get the peak of the Earth emissions, which comes to 0.6 times 20 is about 12. So this peak here is at about 12 micrometers, or 10 I'd put there, and that is right in the middle of the infrared spectrum. So we can't see infrared light, but the Earth is emitting infrared light all the time. Now we are in a constant temperature of 300 Kelvin. So we are receiving energy in the form of UV and visible radiation coming in from the sun, but we are also emitting infrared radiation in the form of from the Earth. And you don't need too much paper to work out that the temperature of the Earth should just depend on 3 parameters, something called solar flux, which is really related to how much visible radiation we're getting into the sun, a small term, which is the Earth albedo, which says something about how much aerosol particles absorb or scatter some of this radiation, but that's a small term. And on the bottom, you've got an absolute constant, Stefan constant, that comes about from this first equation here. And the whole of that square bracket is to the 1/4 power. That means you take the square root and then you take the square root again. And I don't want to go into statistics, but even if you've got these three parameters, the values of them are slightly wrong by the time you've square rooted and square rooted it again, you have damped out the errors. So when I say the temperature to the Earth should be about 256 Kelvin, that's using what we think are the right value of F of S, A, and little s, and there's really not much error in that. So the temperature of the Earth should be about 256 Kelvin, let's say plus or minus 1 degree. That's minus 17 centigrade. That is bloody cold. Now, the temperature of the Earth, the average temperature of the Earth is not that. It's about 290 Kelvin, which is plus 17 centigrades. So have we gone from minus 17 to plus 17, which is a change of 34 centigrades or 34 Kelvin? Well, we made that change because what we call the greenhouse effect. And here's a cartoon of what happened. Here's the Earth emitting infrared radiation, and some of that radiation is absorbed by molecules in the first 10 to 20 kilometers above the Earth's surface in the troposphere. Now, I'm not going to go into the details, but about 38% of this radiation is trapped, 62% gets out into the outer world. And once it's been trapped, some of this can be reflected back to Earth. And it is that that causes the temperature to go up. And it's that that leads to an increase in temperature of about 34 Kelvin. And we call that the primary greenhouse effect. It is a really important phenomenon. It makes the temperature of our planet what it is today, and we should celebrate it. So if anybody says to you greenhouse effect, bad news, dirty words, they're speaking absolute rubbish. The greenhouse effect is very, very good news. Now you get a new bit of paper and you do a few more sums, and you can then find out that of that 34 Kelvin, about 30 Kelvin is due to water vapor in the atmosphere. About 3 Kelvin is due to CO2, and about 1 Kelvin is due to methane, N2O, ozone, etc. These, as I say, are the primary greenhouse gases, but you can see here, water is by far the most important. But of course, all we worry about is CO2 and methane. So what's going on there? Now we're going to talk a little bit about which molecules trap this infrared radiation. This is called vibrational spectroscopy. And you probably know that in the Earth's atmosphere, most of it is nitrogen and oxygen. 78% is nitrogen, 21% is oxygen, and the other 1% is everything else. And those two molecules do not absorb infrared radiation because they have what we call no dipole moment. So if you can see my hands, my fists are 2 nitrogen atoms. As the molecule vibrate, that's what we call the vibrational mode of N bond in nitrogen, but that is not infrared active. And it's the same in oxygen. So all the greenhouse effect is caused by residual 1% of things like CO2, not so much water, methane, etc. In other words, the atmosphere is incredibly fragile to the concentration of that final 1%. But the take-home message is that the greenhouse effect is really, really good news. Otherwise, we would live in Siberian temperatures all the time, all through the year. And in fact, the evidence for this trapping goes back a long, long time. In scientific terms, I think the first data was published in the late 1970s, over 40 years ago, and it first was formulated in a standard textbook just 2 years later by Richard Wayne. Now, it's slightly unfortunate, this is a diagram I've pinned from that book. The wavelength is going the other way now. Sorry, I tried to move the mouse around. Try to see. Okay, wavelength is now low on the right and high on the left. So we're increasing wavelength is going to right to left. And the dotted line there are what you see are the black body curves for black bodies of radiation 200 Kelvin, 220, 240, 260, 280. And the satellite going outside the Earth's atmosphere with instrumentation sees the radiation coming out of the Earth. So you expect it to follow these dotted lines at about 290 to 300 Kelvin. And up to a point it does, it rises, goes through a peak and then start to drop when the peak is somewhere around 12 microns. But you see there these big dips, big absorptions. The absorption at 15 microns is where CO2 absorbs. The absorption at 9.5 microns is where ozone absorbs. And everything below 8 microns is where water vapor absorbs. Now, as I say, these are what I call the primary greenhouse gases. They're very important. But it's not what we're worried about. What we are worried about is what I call the secondary greenhouse gases, which could be primary greenhouse gases if their concentration has been increasing for the last few hundred years. And as I'm sure you will all know, there has been increasing concentrations of CO2 and methane since the Industrial Revolution of the started about since 1750. And then there are also new pollutants that absorb infrared strongly in this range of about 6 to 25 micrometers, where the primary gases do not absorb. And into that come things like chlorofluorocarbons, hydrofluorocarbons, perfluorocarbons. These are molecules that didn't exist 250 years ago. So you could say the secondary greenhouse effect is a minor perturbation on what has been there for hundreds, thousands of years, and that is true. But you don't need to get much of a change in concentration of some of these gases, and you cause a lot of problems. So it's the increase in these greenhouse concentrations that cause all the problems. And this is what I call the secondary, or that should be greenhouse effect. And there's lots of numbers in here. Nitrogen, oxygen, water, and then all the trace gases like CO2, methane, N2O, ozone, and all these fluorinated molecules like chlorofluorocarbons. And this is their mole fraction. And you see nitrogen and oxygen make up 99%. Water is a small amount, and everything else is that final 1%. And these are concentrations at the start of the Industrial Revolution and where we are now. And we'd always talk about CO2, where the concentration has gone up a lot from 278 parts per million to 407 ppm. That is a 46% increase. But in my opinion, just as serious is the methane numbers, which has gone up from 0.7 to currently 1.86. So if you think percentage are numbers are important, that is a 158% increase. And I don't want to get too technical, but one molecule of methane causes 30 times as much problem for the future as one molecule of CO2. And in my opinion, methane is going to be just as much a problem in the future as CO2 is going to be. And then working down N2O, ozone, again, their concentration has gone up. And all these CFCs, XFCs, if you believe these numbers, the percentage increase is infinity because they started at 0 250 years ago. And all these numbers are absolute gospel truth, accurate. This came out, for those that want to know, in this journal here, it was published only 4 months ago. Okay, let's talk a bit about CO2. And this is the atmospheric concentration of CO2 at an observatory high up in the mountain in Hawaii. Okay, we just got the last 60 years going from just before 1960 up to 2020, which is almost exactly my lifespan. So I was born somewhere down here and we're now up there. And this increase is absolutely relentless. Let me say a little bit about why you get the oscillations in every measurement. The oscillations come every 6 months according to whether it's summer or winter. And that's basically to do with photosynthetic activity of a vegetation which consumes CO2. And the oscillations do reduce where the data are recorded in regions with a small amount of vegetation, like in the Arctic or the Antarctic, where there are indeed observatories. But there's the increase in CO2. Nobody, not even Mr. Trump, can deny that. But does this relate to the Earth's temperature? Or put another way, does the red correlate with the blue or vice versa? So what does correlation mean? Does red cause blue or does blue cause red? And notice I haven't labeled any axes there. This could be anything, any data of 2 sets of data sets, red and blue. Now, I'm sure some of you will know that in fact, red and blue are CO2 concentrations and what we think are the global temperatures. And this, the x-axis is 140 years from about 1880 up to about 2020 at the moment. The CO2 concentrations are hardly any noise there, absolutely rigid. More uncertainty, of course, in the global temperatures. It depends what the weather was like, where you make these measurements. Huge amount more uncertainty. And this picture, in fact, came from the States. And the States, bless them, work in Fahrenheit. And so 1 Fahrenheit is equivalent 0.56 centigrade. So you can see that we've gone from about minus 0.7 to about plus 0.9 or 1. So we've already risen 1.9 Fahrenheit or about 1.1 centigrade since the start of the Industrial Revolution. And the current figures are that if we reach 3 degrees, the runaway greenhouse effect will probably happen, and then it becomes incredibly serious. Now, let me say a little bit about what I understand the runaway greenhouse effect is. If the temperature goes up, then you all know there is more water vapor in the atmosphere. If there's more water vapor in the atmosphere, the primary greenhouse effect will mean that temperature go up, which means that there are more water in the atmosphere, which means that temperature goes up, and it just cycles on and on and on. And that's what my understanding of what the runaway greenhouse effect is. In other words, the point of no return. And that is the basis of the Paris Agreement of 2015, where all countries are working to try to limit the rise to 1.5 degrees. Initially in Paris, it was 2 degrees with a sort of aspiration that they might get lower than 2. Another world conference in, I think it was Taiwan, 2 years later in 2017, said 2 is not good enough, we've got to get to 1.5. And that is the figure that all countries are working to. And we've already got the 1.1 degree there, okay? And I say nearly all countries, we all know who is the biggest culprit of the lot, the other side of the Atlantic. Even China now is going to be working towards this figure if they possibly can. So I've talked about molecules absorbing infrared radiation. Those of you that do any maths will understand this equation here. It's a differential equation that says the change in something called mu, which I call the dipole moment of the molecule. When you change x, which is some coordinate of bond length or bond angle, the mu by the x must be non-zero. In other words, the vibration must somehow change the dipole moment of the molecule for it to be infrared active. Now, CO2 has 3 vibrational modes. They're called nu1, nu2, and nu3. And it's in fact nu2 that is the biggest problem, simply because it takes place near the peak of the radiation curve of 12 micron. There's a lot of radiation coming off the Earth at 15 microns. So this vibration is one that causes all the problems. And what's actually happening is the molecule is going like that. It's doing that about 10 to 13 times a second, or each vibration is about 50 femtoseconds. And the dipole moment change is in this axis perpendicular to the OCO axis. In spectroscopy language, we call that a perpendicular vibration. And I can assure you that that is the one that causes all the problems. To go to the other end of the spectrum, I got into this whole subject by, you won't believe this, I did get in this subject by accident. I was studying this molecule here for a completely different reason. And it turns out that it is a very new greenhouse gas. It is a CF3 radical joined by a sigma bond to an SF5 radical. It's got 10 atoms in it, and you can work out it's got 24 vibrational modes. But in fact, only 6 of them have any significant infrared intensity, because only 6 of them change the dipole moment of the molecule. And Mike Park was an excellent PhD student 15 years ago with me, and he did these calculations using what is now pretty standard ab initio procedures on the web. And these are the 6 vibration modes, 1, 2, 3, 4, 5, 6. They all range in the range of 500, 1500 centimeters wide was one, or 7 to 15 micrometers. And we call that the atmospheric window, where there's a lot of infrared radiation being emitted by the Earth. And I think it's this one here at 1095 centimeters to minus 1 that we got a simulation of. So carbon is black, sulfur is yellow. The sulfur is surrounded by 5 other fluorine atoms. The carbon is surrounded by 3 other fluorine atoms, and they're joined by a carbon-sulfur bond. And this vibration, let's hope this works. Thank you. This vibration again takes place about 10 to 13 times a second. It again occurred in a region at 9 micrometers where there's a lot of infrared radiation, and there is a big change in dipole moments in that process. So that's the end of the pure science. I could go on for another 3 hours about the pure science, but I won't. I'm just going to summarize and say that the science hasn't changed at all in the last 10 to 20 to 30 years. What has changed is people's perception of the science. And that's what I'm going to be talking about in the second half. Now, my clock says 7:45. I used to play the piano to a much better standard than I do now. And I think I suggest we just have a musical interlude. Just a piece of music takes place about 2 minutes, 2 or 3 minutes. So please take a comfort break, replenish your glass, or just sit, close your eyes and listen to a bit of absolute poetry. See if you can guess who the composer is.
Actually, when you screen share again, Richard, at the top of your screen, you'll find an option called More. And if you disable attendee annotation, that will stop annotations occurring on the screen.
Disable participant annotations?
Yeah, disable attendee annotation, yeah.
Okay.
The top of your screen menu. Yeah.
Sorry.
Yeah, if you skip over the music scale rather than play it, that's it, perfect.
Are you there?
Yep.
Can you?
I can see Murray. We're good.
Okay. Okay. Is everybody still with me? Okay, so that was the last of the 31 variations written by Bach called the Goldberg Variations. It was played by Murray Pariah, who's now in his mid-70s. That was recorded when he was in his mid-30s. I think it's absolute perfection music, and it would definitely be one of my desert island discs if the islands in the Pacific was not submerged because of rising sea levels. So to carry on, I'm prepared to accept the science of the climate change, even if there are still some anomalies. So what are we going to do? And in a sense, the situation is very similar to what our blessed Prime Minister must have been presented with over the last week, when the scientists presented him with the science of COVID and what might happen to the NHS, etc., if nothing was done. Is that okay, Mark? Okay, so what are the consequences if we don't do something? In other words, what might happen if the world temperature does go up by about 1.5 degrees by 2050 or 2100? And as I say, if we get to 3 degrees, that's really serious. Well, with some of this, we've seen already, we've seen the melting poles at both the Arctic and at the Antarctic. We're seeing the rising sea levels. We might not see it on a year-by-year basis, but it's definitely there. And it may lead to tidal surges and some large cities submerge. And this is absolutely true. I was in China 12 months ago, and they gave 3 talks at a place called Hefei University, a big university. And I did say Shanghai might go under. And they were absolutely gobsmacked and shocked, because Shanghai was about 300 miles from where I was. That and Peking or Beijing are the 2 global centers of China, and the thought that one of those might be submerged by rising sea levels, they've just never thought of this. We are clearly already seeing more freak weather conditions, floods and heat waves, both in this country and they're being reported in other countries. And from an ecological point of view, some animal and some wildlife may disappear, which would be very sad. And what is in my opinion, is currently happening now that is not helping? Well, the first one is obvious. America is not yet engaged. Hopefully it might be engaged in a week's time. I get the sense, however, that China, the penny might have dropped, and I think they're committed to do something, I can't remember what, by 2060, whether it's reducing greenhouse emissions, gas concentrations, or temperature, I'm not sure, but the penny I sense is definitely dropping in China. But it's only the young, in other words, everybody listening to this talk, that seem totally engaged by this phenomenon. And it's obvious you guys are going to have to live with the consequences of this. The chances are most of you would live to your 80s, 90s, possibly even 100s. That's another 80 years. That gets us to 2100. Forest fuel burning is not helping, and increasing global population is not helping either. And I'll say more later. Now, the first person, in my opinion, who really got a grasp on this is a man called David Mackay. Here he is in the top left-hand corner. Wonderful man. He was a polymath, absolutely brilliant, whatever he did, and absolutely tragically, he died very young in his mid-40s in about 2016, I think, of some form of cancer. But in 2009, he wrote this book called Sustainable Energy Without the Hot Air, where he really tried to put into simple language global effects and what might happen unless we do something. And he expressing things in these units of metric tons of CO2 per person per year. 1 ton is 1,000 kilograms. And these are amounts of CO2 we can emit if the increase in the Earth's temperature is going to be limited to 1.5 degrees in the next 80 years. Now, there are a lot of numbers here. There's a lot of rounding error, but I'm just going to talk you through these rather carefully. Planet Earth, our population is about 7.6 billion. In 1990, 30 years ago, the average amount that each individual CO2 emits was 4.3 tons per person per year. That's gone up to 4.8. And we got to get that down to under 1 in 80 years if we're going to limit the temperature to 1.5 degrees. So that's just an average figure of the whole of the population. Now, half the population is in China, India, or combined countries of Africa. And those are the stats. And those three numbers add up to about 4 billion, which is roughly half the world's population. China has gone from below the average 2 tons per person per year to well above the average, as China is trying to catch up and become a first world economy. India is also trying to catch up. The rise is not so steep. They're still below the average. Africa has hardly changed at all. We live in Europe. The population of the Europe, we're still in the EU, by the way, is 510 million or 0.51 of a billion. So overall, the average in Europe has gone down from 9 tons to 7 tons, which is not, it's down, but we're still way above the average. In the UK, we're about 1/7 of the population of Europe. We've come down from 10 tons to 6 tons. So we're getting there. America, of course, is way out in front. It's gone from 20 tons. It is coming down, but not much. And Russia is also coming down, but not as much as you might think. Now then, this is a diagram I'm very proud of because I made this diagram myself. I took all the data. It took me about 2 weeks to get all the raw data and produce this diagram. And it basically tried to say what's happening to these global averages of CO2 from 1960 to 2018, so 60 years. And the black line down the bottom is that global average from 4.3 going up to 4.8. And I've taken 7 different countries. America is top of the list. It's gone up to about maximum of 22 tons, and it's now down to about 16 or 17. Russia has come down from its peak up there, is now at about 12 tons. Germany is an interesting one because Germany has also coming down, but it's still at 9. It's still way above the global average that we're trying to get to. And everyone thinks of Germany as a very green country. You know, the green movement is very strong in Germany, and yet the stats are very clear. They produce all their energy now from coal, not from nuclear, because they got out of nuclear in 2011 after the Japanese disaster. And if you like, they're paying the price. I'm sure Mrs. Merkel realizes that because she's a scientist, but she doesn't say that very often. Here's Britain, good old UK, is coming down here. France is also quite well doing quite well. And if I had to put any reason for that, why France and UK are doing quite so well, I think the UK is doing well because we now get a lot of our energy from offshore wind farms. France is doing quite well because it gets a lot of its energy from nuclear establishment. I'm not saying that as good news for nuclear or bad news, whatever, it's just a fact. You can see China's got this big slope going up and India is down here. So that diagram is in this paper that you get the proof of. That's the one I'm most proud of because it's my work. It's not nicked from anybody. If you don't think about people, but just think of countries as a whole, this is a picture I did nick off the web, is here. The side of the sphere is obviously the amount of CO2 they produce. And what you see, China and America are the biggest, about the same. But of course, the population of China is about 3 to 4 times that of America. So that's why the per person per year amount in America is 4 times what it is in China. And I'm never quite sure whether it's this diagram you should look at where you look at total country, or it's that diagram you should look at, which is per person per year. There are pros and cons of both. But we now know how much CO2 is being emitted. Here's the figure down here for the calendar year 2018. I don't think the figures 2019 has yet been published, but it'll come out very soon. It'll be bigger than that, I'm sure of it. Now, CO2 is one way to look at the problem, how much CO2 we emit. The other way to look at the problem is how much energy do we use? And the first thing to say that emission of CO2 is not the same as usage of energy, but they're similar, and we both want to be low. And going back to Mackay in 2009, when he wrote this wonderful book, he now talks about using different units of kilowatt hours energy usage per person per day. And in 2009, the figure he was quoting was that the average person averaged over 60 or 70 million, was 125 of these units. There was an act of parliament in 2008 to reduce this. It would modify it in the last weeks of Theresa May's premiership and say we now must reduce this to about 10 within the next 80 years. Now, these are very, very broad brush figures, but what Mackay was saying 11 years ago is what we as individuals can do. And these are very much approximate savings with huge errors in the numbers. But he reckoned if we turned down thermostats in houses and wear more clothes, we might save about 20 kilowatt hours in 125. If somehow we could modify our means of short distance transport, and I'm sure we all know what that means. It means walk and bike and roller skate and that sort of thing, not get into a car. That might, again, make about 20 units of kilowatt hours per day. If we got out of meat and became totally vegetarian, that might save 10. Then doing the things that everybody got very hot on, not upset, very interested in doing a few years ago, changing all the light to LEDs and keeping old gadgets and not replacing your PC every year. The figures, according to Mackay, are small. Might make you feel good, but it doesn't do much good. But here's the big one: stop flying. And in 2009, he reckoned that might make about a quarter of the difference. And so you either put your thumbs up and you say, of course we could do that, or you cry. Can we really stop flying? I don't think we can. But we can modify what we do, certainly. And what, as individuals, we have less control over is avoid packaging, plastic, buying what I call clutter, or what he called clutter. So these are big, big savings. And I'm sure these numbers, well, I know they're all out of date. And if the poor man had lived, I'm sure he would have produced a second version of this book, and all these numbers would be modified. But as I said, this is another way of looking at a problem. Don't worry about how much CO2 we're emitting. Think about how much energy we're using. So what are we going to do? That's the title of my talk. The first thing to realize is nobody can cop out. This is everybody's problems. And in broad brush figures, we have 1% of the world population, but we contribute 2% of global emissions. It's not surprising, we're a first world developed country. So your country needs you. And you can do all sorts of things like I do. I go on charity bike rides. This was about 5 years ago when I'd just done my first 100-mile charity ride. I got around, I think, in about 7 or 8 hours. I'm very pleased about that. But that's not really going to make much difference. I mean, it feels good, but that's about all. But I do think we should concentrate more on the demand side rather than the supply of energy or carbon. And that can be painful because it's then saying what as individuals people should think about doing. But even in 2018, I think there are reasons for cautious optimism. This is purely my own view. There are some people that who are just morose depressors who just are guilty about the past. The past is gone. We are where we are. We are not going to get anywhere by just morosing about what has happened in the last 300 years. I think that realization is starting to get through. I'm very glad to say that the language of carbon trading, where you pass your emission from one country to another emission to another country, that is disappearing for the simple reason it is immoral. This is a global problem, and you do not change a global problem by handing the dirty something to another country. And it's doomed to fail. It won't get anywhere. I'm a scientist, and I'm in my mid-60s, late 60s. So I've seen examples how science and politics can work together. I haven't talked at all about the stratospheric ozone problem. That would be another talk in itself. But since changes were made, were conventions, laws passed, the ozone problem will be solved. Whether it's solved by 2050 or 2100, I'm not sure, but all the trajectories and the predictions, the modelers say it will be solved, and we will not have ozone holes, not over this country, but over the Antarctic or the Antarctic, or Arctic or Antarctic. And more recently, I think the air pollution problem is now being addressed by many countries in the world, our country included. Fourthly, the cost of green energy, especially solar and wind, is falling very fast in this country. And I really hope that some government has the guts to make a stab at tidal energy, because we are an island. The tide goes up and down twice a day as night follows day. We never know when the sun's going to shine or when the wind's going to blow, but tide is going to happen every day, every year, every day for 80 years. Some government's got to invest some money to do something about this. I live in hope that that will happen. And the fifth point, some may agree, some may not agree. I think there is still realization that fracking is certainly not going to be the answer. And I'm really not sure about nuclear. I'm on the one hand this, on the other hand that. I just do not know. France has gone one way, Germany have gone the other. England is on the fence at the moment, and to be fair, has been for about the last 20 or 30 years. It cannot make up its mind. So what I'm now going to suggest is things we might think about, but I'm a human being. These policies cannot apply to the young, the old, the disabled, or the ill. And officially, I'm one of those third people. I'm disabled because I've been shielded for the last 9 months. So if I'd obeyed the rules strictly, I would have not gone out of this house. Well, I've broken the rules. Doesn't worry me at all, but you know, there are a lot of people who fall into that category. But of the 150 to 200 people listening to this, I suspect most of you will fall into this. 50% of the population do not fall into these groups. You know, I hope you're all very healthy and remain healthy all your life. So anything I could suggest has got to have has got to have exemption for these categories of people. But that still leaves a lot of people who could do something about what I could suggest. Now, I'm sure you're told in schools that if you've got a big problem, you should break the problem down into simple, medium, and then difficult, and take it step by step. And I'm going to do the same with possible suggestions of what we could do about this CO2 problem, greenhouse gas problem. And so if by some miracle, this was my home here, which means I was Prime Minister, God help you all. But what I would do, I would reduce the working temperature from 70 degrees to 15 degrees and wear more clothes and more old clothes. And very deliberately, I have put on this red jumper. It's a bit dirty, but you won't worry about that. This was knitted by my wife 6 months before we got married 35 years ago. It's got a few holes in it, which have been patched up, but here it is. It's still going strong. Now, I won't live another 35 years, but this is a joke, but I do say this quite seriously. Turn the temperatures down in your houses and wear more clothes. Being more serious, I hope some Prime Minister would price domestic air travel in England out of the market. Now, what I mean by that is not abolish flying or abolish airline, but stop people taking an aeroplane, let's say from Birmingham to Edinburgh. Because if you really think about Birmingham to Edinburgh, that's about now 4 hours on a train from the centre of Birmingham to the centre of Edinburgh. The flight takes about 1 hour, but by the time you got to the airport, clocked in, scanned everything, got out at the far end, got into the centre of Edinburgh, it's at least 4 hours. So why do people do this? Because it's not time, it just does not add up. With a huge expansion of train travel and safe cycling routes. So I'm a great fan of HS2, and I hope there's HS3 and HS4 and HS99 if it gets people out of the aeroplanes for flying around this country. And I would retrofit all houses, providing us free double glazing and roof insulation. Some of that is happening, and some it may well happen much more in the next few years. I think it will. So we're working towards that. And then we get on to the medium difficulty problems. So I just put two possibilities. Carbon tax via credit cards. The principle here that if you pollute, you should pay. Pollution could mean using more energy in your house. It could mean driving 10,000 miles rather than 5,000 miles. It could mean flying from Birmingham to Edinburgh, but you must pay. And my sense is that Canada wanted to go down this route, but they bottled out. But I'm sure many countries want to do this, but nobody wants to be the first. But if one country take the lead, I think others would follow. Perhaps it will be New Zealand. They have a new young prime minister. It's just the sort of thing she might do, I think. So I feel very strongly about that carbon tax in some shape or form. Food policy, I don't want to talk much about, but just think about what we eat and where it comes from, and you scratch your head and say, this is crazy. Why do we transport meat, margarine, fruit, vegetable all over the place so that we can get what we want on our plate? It's because we want to be able to eat what we want every day of the year as if there's no tomorrow. This comes at a price. And then what would be really difficult to implement in the UK? Well, we're not China and we haven't yet got a population policy, but should we perhaps have? Could we possibly limit access to the welfare state for large families? I can see somebody straight away saying, define large, Richard Tuckett. What happens if I've got twins or triplets, blah, 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 on it would go. But something could be done if they really wanted to control population, if you thought that was the big problem. And then to take this one step forward, what about world population? Is world population an important issue? And the numbers stark. 1964, the planet had 3.3 billion. It's now 7.6, 7.7. Who knows where it's going to be in 80 years' time, but somewhere, I suspect, between 9, 10, or 11 million. And there are two counter arguments on these contentious issues. There's what I call the David Attenborough argument, population matters, which say, well, it's bloody obvious we've got too many people on this planet. Do something about it. Don't have kids or have fewer kids. Stands to reason. The other argument is one that was and advocated by George Monbiot in The Guardian, whether he still does, I don't know, which says all the problems of large families are in Africa and Asia, where the standard of living is low, where the numbers are, these are not the people that are using energy or producing greenhouse gases. Stop banging on about the countries where there's not a problem. The problem is in the developed West. And in a sense, both of those arguments are scientifically and factually correct. And which side is like a piece of string? Where do you lie on this piece of string? Yeah, do you lie at one end or at the other end? If you think it's an important matter, could the UN lead on this matter? I don't know. All I can do is just throw out ideas. And this is my last slide. So I've said this before, this emergency effect is going to affect every single person on this planet. And just think about this. I am certain that if it really gets hold, there will be mass migration from the low-lying islands and countries in the southern hemisphere to the higher-lying northern hemisphere. The well-off countries in the north will be swamped with people. And we're going to have to cope with that. If I had 3 dreams for the next 50 years, there they are. I would hope that somebody would make it possible so that we could fly to China or America without using any energy at all, but it could all be solar powered. I have no idea whether that's pie in the sky or whether it's possible. Number B, I would love somehow if we could transport solar energy for where it is produced in the low population deserts around the equator, especially in Sahara, to high population areas in the northern hemisphere. That would be fantastic. And I think there is quite a good chance that technology will happen in the next 50 years. And thirdly, if somehow we could trap CO2 and CH4 either underground or in space. Now, I've not mentioned much about methane, but I do again believe that it is every bit as serious problem as CO2. And so issue to everybody in the UK should think about, especially the people listening to this webinar, please think about flying less. I'm not saying stop flying, because if you want to go to a country that is across a big sea, you have no choice, but do think about flying less for weekend hops to France, Germany, whatever. Drive your cars less when you pass your driving test, and walk and cycle more. Eat less meat and more vegetable and fruit. And I hope none of you got children, but when you do think about this in 10 to 15 to 20 years time, just think about possibly having fewer children than you might have done. Now, I could be put up against the wall and say, Richard, what have you done? Well, on A, I do fly less. I will go to China, not to America. Within Europe, I will only go by train now. I do drive a car less. My wife and I, our kids have left home. We used to average 10,000 miles a year. It's now below 5,000, and that's not just COVID either. I cycle, I'm an avid cyclist. I think I average about 3,000 miles a year. I've become almost totally vegetarian and feel very healthy for doing that. And people should not just think about meat, just think about dairy products, think about milk, margarine, cheese especially. These are high producers of CO2 emissions. I have 3 children. I'm past that stage of my life now, but I think if I'd been in my 30s now, I think I would have thought quite hard about having a 3rd child. Still, every person and every country must adapt in the most appropriate way that they think appropriate. So to conclude, you will all get proofs to this chapter within a few days. There may be some typos, but basically it is as a chapter will be. You should be able to understand the first third and the last third, and the middle section is more sciencing and is likely to be beyond everybody here. Sometimes it's beyond me, even though I wrote it. And finally, I submitted this chapter in February of this year, 1 month before COVID struck the UK. Or what is so interesting in retrospect is that so many of my suggestions for greenhouse gas control are exactly the policies now being asked of everybody for COVID control. For example, work from home if possible, travel less, walk and bike more. I could go on for another hour. So let's just hope that the lessons of COVID can be fast-tracked to coping strategies for the climate emergency that will soon be upon us if we do nothing.
Excellent. Well, thank you very much, Richard. We do have a few questions that have come up. So should we do the questions first, Jill? Is that...
Yep, that's fine.
Okay, so excellent. So first of all, coming up, the first one is, you mentioned methane, you mentioned CO2. The question is, why is methane worse than CO2?
That's a complicated question to answer simply. Methane has got 5 atoms, so it has got it's got 9 vibrational modes. So CO2 has just got 2 vibrational modes that absorb infrared. Methane has got about 4 or 5, I think. It all depends how strongly they absorb infrared radiation, at what wavelength. There is a thing called the global warming potential, which is complicated, but it's an amalgamation of how strongly a molecule absorbs infrared radiation, what the rate of increase of its concentration is, and what its lifetime is in the atmosphere. Now, in that sense, CO2, you might think, would win out because it's got a lifetime in the atmosphere of about 100 years, whereas methane is about 12 years only. But when you put all these numbers together, whoever asked this question, go and Google global warming potential of methane and CO2, and you'll find that everything is referenced to CO2, which has got the value of 1, is a dimensionless number. Methane's value changes about the place, but the figure is somewhere in the 20s. I think it's about 28. And what that is saying, over the next 100 years, on average, 1 methane molecule will cause 28 times as much problems as 1 CO2. But why we talk about CO2 so much is because there's so much more CO2 at the moment in the atmosphere than there is methane. Does that, I don't know, is that?
Excellent. No, thank you, Richard. That's good. A few more questions. Well, someone's asking me what undergraduate degree I did. I did a BSc in chemistry with industrial experience before going into industry, then returning to do a PhD in chemistry. So my background is very much chemistry as well. Another question here. How has renewable resources helped to curb the impact of climate emergency? And perhaps you could include nuclear as a green energy source there as well, Richard. So
Sorry, can you repeat that?
Yes, how has renewable resources helped to curb the impact of climate emergency? I think you mentioned our offshore wind farms, for example,
yeah.
Also,
well, I think it is helping. It is helping. There's no doubt about it. The cost of solar and wind energy is coming down fast. The great thing about nuclear is that it's carbon free. That's the great thing about it. There's no carbon emissions once it's up and running and producing energy. There is, of course, the risk of nuclear waste and what you do about that. Now, I do not know enough about this at all to know. So I sit on the fence. Mark does not sit on the fence, I think. The one big one for me is tidal energy. You know, we know there's going to be 2 tides, high tide twice a day, day in, day out. You know, just night follows day. I just wish some government would. They can find the money to cope with COVID in the billions. And I can't remember how much they said they couldn't go ahead with the Swansea trial barrage because it was so many millions, I think. I mean,
absolutely, I agree, Richard. I've always said tidal. We've been predicting the tides, as you say, we're in Ireland. Wales uses hydroelectric power to produce energy when it's required. So the technology is there. I think with the seawater, it is an engineering challenge. It's a very corrosive environment. There are challenges, but they shouldn't be unsurmountable. And I think you're right. Tidal, of all the renewables, is the only one that we can actually predict the energy flow. So that's very true. Yeah. Excellent. So moving on. Someone's asked, what is your opinion on the Green New Deal that was proposed in the US Senate. I don't know if you know anything about the Green New Deal.
In the US Senate?
Yeah.
Well, I didn't. Who was it proposed by? By the Democrats, I suppose.
I would imagine the Democrats. Yeah.
Yeah. Well, just in the same way, I'm all in favor of it, just as I am for the Green New Deal in this country. That's a phrase I thought was associated with the Labour Party in this country. But yeah, as broad brush, I'm all for it.
Yeah, excellent.
I'm sorry, we've got to get out of this country thinking that our economy is based on coffee salons, sandwich bars themselves. And we've really got to get these people into jobs like retrofitting, green jobs in the broadest sense of the word. Now, okay, that is political, but I mean it very seriously.
Excellent. Question about responsibility. Do you think that the responsibility of the climate emergency should be placed more on individuals, governments, or large corporations? I.e., will many individuals making these small changes in our lives make the difference, or is it more affected by the people in charge?
No, it has to be the people in charge. You know, what you do, Mark, or what I do, or what anybody does, really, we're just dots in the sand, one bit of sand, that's all. It might make you feel good, but if you really think you're going to solve the climate emergency by stopping driving one car and biking everywhere, you might feel very good about that. It's not going to make it any different. It has to be government, and not only has to be government, it has to be cooperation between government, which is why Paris was so important, and why Glasgow next year is going to be just as important.
Excellent. Talking about cars, do you think that electric cars will play a role in reducing carbon emissions? So the electrification of our transport?
I don't know. I just don't know. In terms of carbon, it all depends where you start the counting.
It depends how you produce the electricity. If you're
Yes,
using electricity,
sure,
how is that being produced?
Sure. I think what I say in this in this chapter is word effect, just drive less. I'm not saying get rid of cars, just drive less if it is possible.
I think also we're thinking about electrification, and there's technology and new batteries, lithium-ion rechargeable batteries, etc. But in the future, I'd like to see maybe the hydrogen economy taking off and using fuel cells to produce electricity. That's something that might help in the future as well.
Is that a question, or are you saying that?
Oh, well, that's my personal opinion. But
yeah, sure.
If you agreed with that one.
Sure.
Question about you. So you mentioned the sort of solar power. Someone here is saying, I've been talking about solar power energy transportation among my friends, and the major rebuttal they have is the financial barrier. So is there a financial barrier to sort of using solar energy? I know that the photovoltaic cells use expensive materials and rare earth metals, but what do you think about the cost of those solar power?
Well, I think the cost of PV is coming down sharply. But that always happens as you've developed something new and more people buy these things, the cost always does come down. Think of mobile phones. They were prohibitively expensive 20 years ago. They're now very cheap, really, relatively speaking.
Yeah, I think also photovoltaic cells, they get less efficient the hotter they get. So a hot sunny day is not necessarily the most efficient way to produce electricity, and maximum about 20% aren't they? So we need to increase the efficiency of solar panel if we're going to use it. And I think we're going to be mindful about where we get the elements to make the materials from, the rare earths, as their name suggests, they are in short supply. So I think finances will always be part of that. Interesting to see that sort of China has a monopoly on a lot of the mines as well that produce these minerals. So I think finances will play a part in the future. Interesting question here, Richard. When will the effect of climate change be irreversible? If it will. So will they get to a stage where climate change is irreversible?
Well, in scientific terms, is when the runaway greenhouse effect gets going. And whether that's when we get to 3 degrees or 4 degrees or 5 degrees, I just do not know. The impression I'm getting is that most people think we will not hit the 1.5 degree target, let alone the 2 degree target. It'll be more like 3 degrees. I just don't know enough to know when the runaway greenhouse. I'm not a modeler. All I can do is just read what other people write, think about it, and try to interpret it.
I mean, one comment, when you mention temperatures like an increase of global temperature of 1.5 degrees, most people on the street might think, well, that's a very small temperature rise. Surely that won't make much difference. Because we've got to realise that the majority of our planet's covered in ocean water. Water has a high thermal mass, as you know, Richard, and it actually takes a lot of energy to then produce a small temperature rise in water. So actually our oceans are absorbing a lot more energy than that temperature rise would indicate. So I think sometimes talking temperatures, people don't realise the amount of energy that's actually going in, do they sometimes?
I think the other thing I would say is that this ballpark figure about the temperature of the planet, it all depends where you measure it. And some people think this is the wrong thing to concentrate on. We should think about much more the temperature of the oceans and the acidity of the oceans, because I'm not sure the numbers. Do they cover about 80% of the land mass of the surface of the planet Earth? About that.
Certainly Australia is worried about the acidification of the ocean as you dissolve the carbon dioxide in it, because you now have an acidic solution that's dissolving coral reefs and having other effects as well. So that feeds back to the ecological points that you mentioned as well. Okay.
Well, perhaps I was just wondering, Mark, just watching the time, and perhaps people have to go. So perhaps I could just say thank you very much to Richard. He gave us an excellent overview, clear presentation of obviously a very complex subject, but also give us a number of things to think about ourselves, even though perhaps individual things don't have a big effect, but perhaps something that everyone can think about as well. And also, could I just remind everyone that the next lecture in 2 weeks' time, on the 17th of November, is Elements by Sir Martin Polyakov. So if you haven't signed up, I don't know if there's any more tickets available, but there may well be. It's worthwhile having a look. But thank you very much, Richard, for all of that. And thank you, everybody, for coming. Thank you.
Thank you.
Excellent. Thank you very much, Richard. Thank you for that. And thank you, Jill.